Hello. So now that we know how to compute the friction head loss and knowing that there is laminar type of flow and there's turbulent type of flow, let's do some problems. So in this one you have two reservoirs that are connected by a pipe. The fluid is ethyl alcohol and you have very large tanks so that the level in the tank stays constant, doesn't drop very fast. So the question is, in this case, what should the flow rate be in meters cubed per hour? And it asks you if the flow is laminar. So let's, we want to find the flow rate that will go through this pipe from the top tank to the bottom tank. Given that we have a pipe of diameter 2 millimeters, and the length of the pipe is 40 plus 80, 120 centimeters. So the fluid properties are given. You can find them in the table. And now let's do the conservation of energy for a control volume. So let's pick our control volume. So I would pick this as my inlet to the control volume and this as my outlet. Primarily because a water or ethyl alcohol particle will come from the surface at zero velocity. Its velocity is going to increase, then go through the pipe. In the pipe, its velocity is going to be constant due to mass conservation, and as it leaves the pipe and its velocity is going to drop until it hits the top surface where it gets a zero velocity. So if I pick this as my inlet and this as my outlet, the two free surfaces, I know the velocities and the pressures due to the atmospheric conditions, so it makes life easier. So let's do that. And obviously, this is my first law of thermodynamics. I don't have a pump. I wouldn't have a turbine. Here's the thing that you want to think about. Do we have friction in this system? They don't tell you it's they don't tell you that there is friction in the system. And this is your clue in here is you have a pipe of diameter d and length L. So anytime you see a pipe of diameter d and length L, automatically you have to think about friction. So we do have friction, we cannot cancel it out. Then as we said, at the outlet, my pressure is atmospheric. And due to the large size reservoir, mass conservation tells me it has zero velocity. And at the inlet, pressure is atmospheric, and it's still a large reservoir. So I end up with the friction. So here, let's take a fluid particle that came from here, went through the pipe, and all the way until it got to this point. So it has gravitational energy associated with its height above a certain reference. That particle accelerated. So three things are happening at the same time. Its height, gravitational altitude, is getting less and less, and its velocity is increasing, and its pressure, at least in this region, its velocity is going to increase, and the pressure is going to vary. And in the pipe, we know that the velocity stays constant. While in the pipe, there is friction that the fluid faces. So a lot of that energy, all the energy that the energy difference between those two levels, so the fluid particle will continue until it hits the surface, and all the energy that was used, or the energy contained in the particle at this level was lost through the pipe, friction in the pipe. So that's what this equation tells us, is that all the energy stored due to gravity was lost in the pipe, and Z1 minus Z2 is this 40 it's distance between the two levels, and it's 40 plus 50, so it's 0.9 meters. So now we know what HF is. It's 0.9 meter. That's the friction head loss. And we know that the friction head loss is related to the velocity in the pipe, the type of fluid, the velocity at which the fluid is moving, but we don't really know how fast the fluid is moving. They ask us to find the flow rate going through it. So if we don't know the velocity, we wouldn't know whether our flow is we wouldn't know our Reynolds number, and we wouldn't know whether the flow is laminar or turbulent. So let's try and just have. So we need to guess our flow regime, whether it's laminar or turbulent within the pipe. And there are multiple ways of doing that. You can just come up with a number out of thin air, but that's not the best way of doing it. Here, let's take the case where I don't have friction. And we know from Bernoulli that the maximum velocity associate. So let me just get my eraser here. Now, if I take the pipe and just extend it. So let me just show you what I mean. So here's the scenario that we're really looking at. We're looking at the scenario where imagine that your pipe is doesn't terminate at the bottom, and now we have a frictionless type of flow, but ends at the surface here. So now if I ask you to find what the velocity that comes out of the pipe is going to be, it's going to be square root of 2gh. And that's when I don't have friction. So that would actually be the maximum possible velocity that we're going to get through the pipe, assuming that there is no friction. But obviously it's going to be much less. But let's take it at face value, 4.2 meters per second. I should have taken it less than that, maybe half, because friction is significant, but particularly that we're talking about a very a capillary type of pipe, which is 2 millimeters in diameter. That's very small, very fine. But nonetheless, just for the sake of demonstration, we'll stick with this initial guess. That gives us a Reynolds number based on the diameter of the pipe, using the velocity of 4.2 meters per second, and the density and viscosity that are given up here. A Reynolds number of 5,500, so that is turbulent because it's above 2,300. So now we have our Reynolds number, and we know that the flow is turbulent. Well, that gives us that the flow is turbulent. So let's go to Moody Chart to find the F. So bear with me here. So here's my Reynolds number, 5,500, and I have a choice of curves to go through or to pick from. So I would, since this pipe is very small, 2 millimeters, I would imagine that it has to be very smooth, made out of glass. So I would pick something closer to the lower end. And I just decided to, you see, we are still in the guessing phase. We don't know if it's laminar or turbulent, so we have some leeway in our solution. So I've picked it 0.05 as my friction factor F, the HF L over dV square over 2G. And so now we have two options, either to compute an HF and compare it to our correct HF, or compute a velocity and compare it to, with this HF, what velocity would give us this friction factor. So I've decided to just actually use the velocity in here as known, the guessed velocity, and I decided to just compute the HF. So you compute an HF, we have the F 0.05, we sort of guessed it from the Moody Chart, length L over D, and the velocity is the one that we, the educated guess that we started with. So that gives me an HF for these conditions of 27. That's much, much larger than the 0.9. So what does this 27 meters tell me? So that has units of 27 meters. It tells me that if I have a turbulent flow with a friction factor of 0.05, and I am moving, or if I am a turbulent flow and I'm moving at 4.2 meters per second in this pipe, at this epsilon over d, which is associated with a friction factor of 0.05, I'm going to face a friction of 27 meters. So that's completely unphysical at this number. So it means I need to be at a much slower velocity because the true friction head loss, that's the maximum possible, just because it's the gravity that's driving the flow, cannot be above 0.9. That violates the second law of thermodynamics. And even the first law. So the 27 doesn't make sense. It's too high. So my initial guess is too high, the 4.2. So I'm gonna guess it's maybe 1/3 of that. So that takes me to maybe 2,000 or 1,500. And that means I'm going to be laminar. So I'm going now to jump back to a laminar guess. So my initial guess was bad. And for a laminar flow, there's a relationship between the friction head loss. In fact, it's this curve, F is 64 over RE. So you can just pick that. And you rearrange and you get an HF of 32 times the viscosity, length of the pipe, average velocity by rho g times d squared. And from this we get a velocity of 0.6 meters per second. Compare that to our initial guess. We're very far off in our initial guess. And that gives me a volumetric flow rate of this much meters cubed per second. So that is the flow rate that this kind of system can sustain. And if you try to solve this again and make the pipe wider, you're going to get a larger flow rate, most likely. And if you make the pipe thinner, narrower than maybe a millimeter, you're going to get much less flow rate. Okay, so moving on, and we said, okay, so let's check so now we said let's guess that our flow must be laminar, and now we have the velocity. We can check with this velocity what our Reynolds number. It's less than 2,300, so it's great. So our guess is fine and stuff. So as we said at the beginning of this chapter, we have two types of problems that we are going to face. The first set of problem is we are able to compute Reynolds number, so we know the pipe diameter and the velocity of the flow, which is the easiest type of problems, and these do not require iteration. But there are design problems or analysis, off-point analysis problems where you don't know, so you're asked to find the diameter of the pipe, to design and spec what diameter you should get, or where your velocity is unknown, that you need to get, just like we had in the previous example. So in situations where you can't get Reynolds number at the onset, you don't really know whether you're laminar or turbulent. Your flow in the pipe is laminar or turbulent. So you have to do some iterative, you need to do the iterative solution. And that iterative solution, you start with an educated guess, just like we've done, and it doesn't work always 100%, as you've seen in the previous example. It's really like your educated guess helps you minimize the number of iterations that you need to go through. So here is how this process of iteration goes. So you guess So as we said, you either don't know the velocity or the diameter, which means you don't know what your friction factor is. So you can guess any of those. You can guess either the velocity or the diameter, or guess the friction factor. So let's say you guess the friction factor, and the reason why I like to guess the friction factor is that the range that we're talking about is not that much. It's between 0.1 for the whole chart, 0.01 to 0.1, so it's just one order of magnitude, and that narrows, that makes your iterations converge much faster. So it's always best to, and if you have to work blindly, maybe you want to go in the middle of the range. You don't really know whether you're laminar or turbulent. I would go maybe mid-range, so somewhere between 0.02, 0.03 friction factor. So now you guessed your F, then you compute if your diameter is unknown, you compute your diameter, and if your velocity is unknown, you compute your velocity. So now you find one of those, and now you have your Reynolds number, and you go to Moody Chart, check at this Reynolds number what your friction factor is going to be. So now you find a new friction factor. So this new friction factor, you compare it to the old, which is the one that you started with, and if the range of difference is less than 10%, then you've arrived. So these two numbers are very close together, so could be 0.1 and this would be 0.11, so it's within 10%, so you're fine, you've gotten to the final answer. Stick with the last iteration. But let's say, just like we had in the previous case, we had a difference of larger than 10%, then you just go again and do the process where you update your F with the new value that you have gotten here. So you take this new F and stick it up here, and stick it in here, and then compute D again or V again, and then compute Reynolds number again, and repeat until you get to less than 10%. Depending on your initial guess and where you are on the curve, whether the curve is steep or it's flat, you can have a few iterations, or you can have 3, 4, or 5 iterations, which is considered a bit long or a bit too many. So that's how you do it. And these are the two types of problems that we have in pipe energetics. Let's do another example. So here you have a tank and a pipe, and they tell you that this system, the pipe has a length of 5 meters and diameter of 3 centimeters, so that's great. And they also give you the flow rate that this pipe is supposed to deliver in terms of water. And the question is, you want to pick the material of the pipe, whether it's smooth or rough. So that's what we want to do. And this is the first kind of problems where we're not designing. We have the diameter, we have the flow rate, so we have the velocity, and we have the velocity, we have the diameter, and the fluid properties. So we have our Reynolds number, so we know whether we are laminar or turbulent. So that makes our life much easier. So to solve this, we want to go through an energetic analysis, so let's see what is given. We have 11 meters cubed per hour, that's the flow rate. We have the density and viscosity. So from this volumetric flow rate, we can get a velocity in the pipe, and we can compute a Reynolds number based on the fluid properties and the geometric features. So let's do control volume analysis, and we want to be able to pick our so for our energetic analysis, we want to be smart in picking our inlet and outlet. So it's it's a single inlet, single outlet system. So I would pick this as my inlet, I would pick this as my outlet. At my inlet I know the pressure and the velocity. Since it's a large tank, the drop in level is very slow, while at the outlet I have my velocity and I have my pressure, and I have the from geometry I have the heights and the levels above a certain reference. So here I need to make a comment, is why is it so, is in all this we're assuming that, or we're going with the notion that the friction is really generated by the pipe. We haven't, so we're implicitly saying that, but now we have explicitly said it. Anytime you see a pipe, that's the major source of friction generation. So let's do the first law analysis on this problem. We don't have a pump, we don't have a turbine. We have a pipe of length L and diameter D, so we have friction. So at the outlet, my pressure is atmospheric. I know my Z, so let's say to be 0. So we'll set it 0. So this is my out over here. And this is my in. At the inlet, my pressure is atmospheric, my velocity is 0, and my Z level is 4 meters. So now you see that the gravitational energy that a fluid particle starts over with right here, this 4 meter gravitational energy, associated gravitational head, goes into two parts. One part is kinetic energy at the outlet, so here, and the other part is that energy goes to friction through the pipe. So if we rearrange this, we have the delta Z goes into friction head loss, as well as kinetic energy coming out of the pipe. So we've computed the velocity to be 4.3 meters per second. You stick it in here. Z1 minus Z2 is 4 meters. So I get my friction head loss of 3 meters. And then I use my compute my Darcy friction factor, because now I have the HF. So I stick HF 3.05 meters. I have the length and the diameter of the pipe, and I have the velocity in the pipe. So I get a friction factor of a Darcy friction factor of almost 0.02. So what next? We want to know what pipe material should we make this out of. So we have a Reynolds number, and we have a Darcy friction factor. So let's go consult the Moody Chart. The Moody Chart tells us that, so the flow is turbulent, and we know that in a turbulent type of flow, our flow can be hydrodynamically smooth or hydrodynamically rough. So we really need to know whether we're rough or smooth. But since they ask us what the epsilon over D is, it's probably going to be a rough type of pipe. So let's get the Moody Chart. So this is our Moody Chart, and we have Reynolds number of 129,000. So this is 100,000. This is 200,000 here. 100,000, 200, 100,000, 200,000, and so we're working along this plane, along this line. We also have the friction factor to be 0.019, so we're somewhere here, right there. And at the intersection, we see that we're between those two curves. Those two curves are the 0.004 epsilon over D. So you see, you take this curve and follow it, right? You'll get the 0.004, and you'll follow the bottom curve, 0.002. So we're somewhere in between, so we can interpolate. So we interpolate, and we get, for this Reynolds number and this friction factor, we get an epsilon over d of approximately 0.0003. It's between the 0002 and 4. So we'll pick it halfway. So we get 0.003, and that's our epsilon over d multiplied by the diameter, and you get the roughness height of the pipe. It's generally a root mean square type value. And let's see what pipe material we can live with. So that's the maximum roughness we can get. If we have a pipe rougher than this, we're going to get to a higher friction factor. And if we go back here to the Moody Chart, we see this is our smooth pipe. This is the only curve that's hydrodynamically smooth, and every other curve is actually a rough curve. But as you go up and higher with the curves, your roughness, relative roughness, is increasing. So we're pretty smooth right here. We're very close to the smooth pipe. A smooth pipe will have a roughness factor of approximately 0.017. We are 0.019, so we are probably within 8% of that. And so let's see what pipe can would fit our bill. Steel, it's too rough, doesn't work. Stainless steel can actually work. 0.002 is less than that, so that's 9 micron. This is 2 micron, that's good enough. And the other one, I'm going down through the list. This will work, this will work, and a glass pipe will also work. So we have limited type of selection, and if you look at a pipe of 3 centimeter diameter, that's going to be extremely expensive to get this type of smoothness and this type of pipe. Plastic, probably your best bet. If plastic is fine, then just get plastic, because it's cheaper than stainless as well as brass. I don't know if they make brass that large, but so you get the idea. And now let's go to the Moody Chart. And the Moody Chart has been, we've started this chapter with round pipes that have a circular cross-section. But in fact, people have found out that we can actually use the Moody Chart with pipes that are of arbitrary cross-sections, maybe a square or triangular or some other kind of shape. However, you need to get some circular equivalent type of diameter. So the Moody Chart is set up for circular pipes, but if we have non-circular pipes, I'm telling you that the Moody Chart will work, except you really need to get some circular pipe equivalent. So we're talking about, here you have 2 concentric cylinders. You see this a lot in heat transfer applications where you have radiators and heat exchangers. So the flow is in an annular type of flow. And what diameter do we pick here? We have the flow between the 2 cylinders. The first cylinder has a radius B, and the second cylinder has a radius R equal A. Or what if we have a rectangular duct? We see those duct of width B and height H, or height here 2H. What kind of diameter, equivalent diameter, should we use to have the Moody Chart work in our favor? Well, there is an equivalent diameter, and it's called the hydraulic diameter. And it is defined to be the cross-sectional area times 4 divided by a wetted perimeter. So the wetted perimeter, it's the perimeter of the pipe, the length. So if you take a cross-section and you look at where you take a cross-section of your conduit, the non-circular the non-circular pipe or duct, you take a cross section and you see where your fluid is touching. So it's touching here and here, and you take the length of that. So it's the that's the perimeter. So if let me explain this a little bit more. So if I take this concentric cylinder, now this is a cross-sectional view or a front view. Let me look at a cross-sectional view. This is the inner cylinder of radius B. This is the outer cylinder of radius A. And the wetted perimeter is this length, because the fluid is touching this solid surface and this solid surface. So the length of those two, this is the wetted perimeter. It's the pipe surface that is being wetted by the material. And if I look at a rectangular cross section, so the flow is going into the page in this case, as well as in this case and this case. So my wetted perimeter is this guy. So it's twice the width plus twice the height of this rectangle. And the cross-sectional area is very easy to, it's the cross-section, it is the wetted also cross-sectional area. So in this case, it's all this area. And here, the fluid is between an annular fluid, it's this particular type of area. This is the white area over here, not white anymore. So let's compute the wetted diameter for the hydraulic diameter for a circular pipe. We'd expect that we should get the same value. The hydraulic diameter should be equal to the diameter of the pipe. Let's guess that. So what is the cross-sectional area of a round pipe? Pi r squared. And what is the wetted perimeter? It's 2 pi r. So let's do that. Pi r squared, 2 pi r, and you have the factor 4. So exactly, we recover the diameter of the pipe, which makes sense. That's how this is how this number was defined. That it has to be an equivalent type of pipe diameter. So if we now look at this case where we have two concentric cylinders and the flow is going between them, we get the hydraulic diameter to be the cross-sectional area, which is the area covered by the flow, which is the pi r1 squared minus pi r2 squared. So this area plus this area, so pi r1 squared plus minus pi r2 squared. And the wetted perimeter is the first circle and the second circle. So this circle over here plus the length of this circle over here. And you get 2a minus b. And for the rectangular duct, you're going to get 2hb, h being the height, and b being the width. Or here it's, right. So here it is half the height, h, but h is half the height. So it is the height of the rectangular duct multiplied by the width divided by the h plus b. So the hydraulic diameter, we only use it with the Moody Chart to get with the formulas for Reynolds number and the friction factor, as well as we should add here the epsilon over d. So in the Moody Chart, this d would be the d hydraulic. The Reynolds number Re, the diameter in there should be the hydraulic diameter. But when you're computing the flow velocity being the volumetric flow rate divided by the area, you take the actual cross-sectional area when you're computing the volumetric flow rate. Okay, so let's deal with this non-circular duct problem. You have a room that's under vacuum, and the vacuum is generated by a fan over here. And the room takes air from outside through a 12-meter length rectangular duct. Actually, it's a square duct, 30 by 30 centimeters. And the question is, if my room pressure is 10 pascal vacuum, so it's 10 pascal below the atmospheric pressure. How much flow rate am I going to get through this rectangular duct? And part B of the problem, what pressure will give you 1200 meters cubed per hour? What should this 10 be? Should it be 15 or 5 to give you 1200 meters cubed per hour? So let's do the first problem, part A. And this is my room, and this is my duct. And here is the properties. They tell you one thing is that it's made, the duct material is commercial steel. And commercial steel, from the table that we have seen, gives you a roughness height of around 50 microns. And we have the aerodynamic properties, density and viscosity. So let's do an energetic analysis. So we need our control volume, inlet and outlet. It's best if I pick the pipe, just because this is my control volume, just because I know my inlet and my outlet. At my inlet, I have the pressure being atmospheric. I don't know the velocity yet, but hold on. And at the outlet, I know that my pressure is 10 pascal, and I don't know the velocity either, but I know because it's the same pipe, I know that the velocity, because the pipe diameter doesn't vary, or the duct diameter doesn't vary, mass conservation will give me the velocity coming out to be the same as the velocity entering at the inlet of the pipe. So let's pick this red control volume as ours. We don't have a pump, we don't have a turbine. It's a duct of length L and some diameter or hydraulic diameter. So definitely we would have friction. The pressure at the outlet minus the inlet is given as 10 pascal. We know from mass conservation that the velocity here at the inlet and the outlet are the same, and we don't know what they are, but we know that they're the same. Our goal is to compute them, and then the Z's, we're going to make the assumption that the geometry is level, so it's a room, so and we don't have a difference in height between the inlet and outlet. So my friction is all the pressure difference provided by the fan goes into friction in the pipe. So I have HF is equal to the delta P, and so here you take the rho g to the left hand side, so the rho g HF is the delta P, and now I can get my HF to be 0.85 meters, and from HF we can get the F. However, so let's see what my F is. I have HF, as you can see here. I have the length of 12 meters. This is the guy. I need to use the hydraulic diameter in this case, because now remember, when we're talking about the friction factor, epsilon over d, or the Reynolds number, it is the diameter that we use in there is the hydraulic diameter. So I need to compute the hydraulic diameter. I don't know the velocity. So we compute the hydraulic diameter just like we had done before, and you'll see that it's a square duct will have the same hydraulic diameter as a of side L will have the same hydraulic diameter as a pipe of round diameter L. So the hydraulic diameter is 30 centimeters. So now I have a relationship between F and V. So F I don't know, and the velocity, so I now computed the hydraulic diameter, you take it, plug it in here, but I don't know the velocity. So I have one equation with two unknowns, so I need to find another equation. So the first equation is my energy equation. So we need to find another equation. We're given in the problem the epsilon, so we can get an epsilon over d. relative roughness. And now remember, our Moody Chart, we have the Moody Chart that relates the Reynolds number to the friction factor, and the Reynolds number has a velocity in it. So let's look at our Moody Chart, and that would actually be our second equation. So here's the Moody Chart, and let me go to the epsilon over d of 0.00153, and it's between 2 and 1, so it's this red curve. So I started from this point, epsilon over d. So this line is my second equation. So I do have a second equation that relates the velocity that's here in an implicit type of relationship with the HF and the velocity that are right here. So in this case, the solution, you can do linear subtraction and between those two equations, the first one, the F, and this guy. So you really need to go through some iterative type of solution. So you start with an initial guess. So I'm going to guess my F is going, so here's how I would do it. I would guess that my F is going to be between here and maybe here. So I'm going to guess my F to be maybe 0.02. And then from that, I'm going to get a velocity, right? So I found my F, I find a velocity. I have an F now. I can compute a velocity. From a velocity, I compute a Reynolds number, and I'll find out that my Reynolds number is going to be here. So my F is too high. So let's say I picked this curve. So my F is too high, and then this would be my corrected F, and I keep iterating. I might go up in the curve again until I get. So you get the idea, and you keep iterating until the initial guess and the final updated value are within 10%. So we iterate to or converge on an F of 0.019, which is associated with a velocity of 4.7 meters per second, and that gives me a volumetric flow rate. Now the second part of the problem is they told us that we have 1200 meters cubed per hour of airflow, and we were asked to find what the room pressure was going to be. So we still do the same control volume, same energy equation. The rho GHF is the delta P. And so we don't have that because we don't have the delta P, we don't have the rho GHF, but I do have the velocity. And from a velocity, I get a Reynolds number, and from a Reynolds number an epsilon over D, so I have a Reynolds number and epsilon over D, 74,000 is somewhere here, that's 100,000, 80,000, that's 75,000 somewhere here. So here's my 75,000, and I go somewhere here, and I will get a friction factor of almost 0.02. And now that I have the F, I will get the HF or the rho GHF, and then I get my pressure. So my delta P between the in and out, or the out and in, is 6.5 Pascal. So my pressure in the room is 6.5 Pascal below the inlet, so it's 6.5 Pascal vacuum. Right, so now the last part that we are going to cover in this chapter is going to deal, so now we have covered round pipes, we have covered when the pipes are laminar, or the flow in the pipe is laminar, and when it's turbulent, and we learned about the flow being smooth or rough in the pipe and what that meant, and we are now able to compute our energetic analysis either using direct explicit solution or using iterative methods. And then we went on to work with non-circular pipes and ducts. We said from an energetic point of view, straight pipes and straight ducts and pipes that are non-circular we'll still are going to work with the Moody Chart in the same fashion, except we have to get a circular equivalent diameter that goes with the Reynolds number, and that goes with the friction factor, and that goes with the roughness, relative roughness height, epsilon over d. And that we call the hydraulic diameter, and this was an example on it. And the rest of the energetic analysis is the same as a round pipe. Now, if you look at a pipe system, at a piping system, so here you have reservoir A, reservoir B, you're moving fluid through from the first reservoir to the second reservoir through piping system, straight segments of pipes, so straight, and here you have a pump that helps you push the fluid against gravity. But also you have those pipe fittings. So you have a valve, you have an entry fitting, you would have some fitting that connects you to the pump, maybe a reducer or an expansion. Same thing here. You'll have elbows, 90 degrees elbows, and so on. You'll have other valves and some exit fitting. And these will introduce friction to our pipe. Remember, so far we have said it's only the pipe, the pipe of length L and diameter D that's going to create friction head loss in my system. But not only. In fact, these pipe fittings are going to generate quite a bit of friction head loss. And we call those the minor losses, the minor friction head losses, as opposed to the major friction head losses associated with straight pipe segments. So we would have, if I have one, let's say so if I look at the pipe fittings, entrance, valve, reducer, so I'll have maybe 1, 2, 3, 4, 5, 6, 7, and maybe 8 pipe fittings. So I sum the energy loss, the minor losses, hydraulic friction losses, friction head losses associated with those fittings, and I would sum them up to the friction head losses associated with the straight segments of the pipe, and that would be the total head loss for my system going, again, if we're eventually doing the energy equation between level 1 and level 2, and the HF, the contributor to the friction head loss, is all these pipe fittings as well as the straight segments of the pipe. So now we know how to compute the HF from a straight pipe. We jump to the Moody Chart, which is this guy. But for a pipe fitting, we have to go to the manufacturer. So the manufacturer will give you some equivalent friction, if you will, friction factor for that particular fitting. So let's look at some of those, and then you sum those friction factors, multiply them by V squared over 2G. So let's look at those friction factors minor friction factors associated with the fittings, elbows, T's, and so on. And the relationship, so the head loss associated with a certain fitting is the K, which is the friction factor for the fitting, multiplied by V squared over 2G, which is the dynamic head, which is the velocity. Typically, that velocity will be defined in the problem. And if I'm having the same diameter pipe that goes with the elbow, it'll be the same pipe. It'll be the same velocity as comes in. But you'll have to look carefully to at this velocity on each plot associated with one of those valves. So you can have different types of valves, fully open, half open, partially open, and so on. And each one would have its own K, depending on the level of opening. But let's look at some examples. So here I have, in fact, here I have two examples. I have a sudden contraction and I have a sudden expansion. So let's look at the sudden contraction when the arrow. So I start with a pipe of small diameter d and end up with a pipe of larger diameter capital D. And I get a sudden expansion that's associated with losses because I get rotational patterns here, vortices sticking around, and they're just eating up the energy and wasting it into heat that is lost to the atmosphere. So they take, they're producing friction, or through friction they are reducing the energy content of the moving fluid. So let's look at the, so if the flow is going from left to right, it would be an expansion. If the flow is going from right to left, it would be a contraction. So let's look at the expansion, and you'll see, so let's look at this plot. It tells you the diameter ratio. When it's 1, you don't have any friction because the pipe is not, there's no sudden expansion. And the larger the ratio, right, larger or smaller, but here it's d over d depending on which one you're talking about. So the farther away from 1 the ratio is, your friction is actually increasing higher and higher. So your K, your dimensionless friction factor for this expansion or contraction is going higher. And we see that in the case of a contraction. So this case, we have actually, you would guess the opposite, but for a certain diameter ratio, a contraction would have almost half the friction head loss at that same speed and same geometry. And it's associated with the flow pattern we talked about over here, the generation of vortices and separation patterns and so on. So it's a complex topic, but for the sake of this lecture, we're just interested in the level of energy waste that happens in that. So let's say we have a contraction or an expansion. First, you look at the geometry, you get the small d over capital D. Let's say it's 0.7, and let's say it's a sudden contraction, and then you get this K, which is our equivalent to F. You get the K multiplied by V squared over 2G. So now which V? That's a good question. And you'll see in this manufacturer has provided the V in the smaller pipe. So you see the V is provided in the smaller pipe. So here you'll see that it's the smaller pipe and in the smaller pipe. So make sure you're very careful with that. We look at another pipe fitting. Here we have a 90-degree bend of certain radius R, radius of curvature R, and a certain pipe diameter D. The flow in this type of fitting is actually very complex, and depending on whether it's 180-degree fitting or 90-degree fitting, such as is the case here, or even a 45-degree fitting, then that's what's plotted over here. So the geometry R over D radius of curvature by the pipe diameter is on this axis, and and the other geometric feature, whether you're one of those fittings over here, here it's only 3 of those is provided. So let's say we're at 7.5 and I'm at 90-degree, or my K is going to be around 0.3. But if I'm 180-degree curve bend, my K is going to be maybe 0.5. And then you take this 0.5 multiplied by V squared over 2G. The V is obvious here, and you get the minor head loss. And that minor head loss, you compute it for each one of those and you sum them all up. and you sum them all up, and you get it just by summing the K. If you have a single inlet, single outlet, single inlet, single outlet, where the flow velocity is uniform across all of them, then you stick with, you can take the V outside. But if not, then you take the V square over 2G inside into the summation. So you have to be careful with this. So with this, we have actually come to the conclusion of our chapter 6 on the analysis of fluid mechanics from an energetic point of view in pipes and ducts. And in fact, we have come towards the end of our material. So here I'm going to make a commercial, an announcement for the second course in fluid mechanics, which we call Aerodynamics MECH314, which is offered in the fall, so you can actually register for it. And it's dealing with, we will start talking about external flows. So we have, in the previous chapter, we have been talking about the flow inside a duct, where we can sustain a lot of pressure. You know, the pressure inside a pipe can be 100 kilopascal, or it can be 5 megapascal. That's a lot of pressure, humongous amount of pressure. But if you're a bird, or if you're an airplane flying in the air, the pressures that we're talking about are actually very small. We're talking in terms of millimeters of H2O. We're talking, I don't know, 10, 20. That's for a huge jetliner, commercial jetliner. We're only talking 10, 20, 30, 40, 50 centimeters of H2O. It's a very, very tiny level of pressure. And the analysis of such kind of systems is going to be different, and that's what we are going to discuss in 516. So look at that, look at the course description in the catalog, and if you want to register for it, you are more than welcome to do that. And you can scan through these slides, and it'll give you an idea of what we're going to start with. So these are the first few lectures, or the first couple of lectures in the MECH314. So guys, thank you for listening. We will post on Moodle a project associated. So now it's not an experiment, but actually a theoretical project to analyze the energetics of a piping system. So wait for that on Moodle, and hopefully I will see you in MECH314. Thank you guys, and I wish you all health. Goodbye.